Hi everyone, and welcome to another short video about working with the Web Audio API, where today we will be talking about the design of graphic equalizers using the Web Audio API. So first, a little bit of background about equalization, starting with a reintroduction of the concept of filters. Filters are audio effects intended to change the magnitudes and the phases of a signal's frequency content. Now, if you've been watching some of the other lectures, you've already seen some audio nodes in the Web Audio API that can be used to create filters. We have the biquad filter node, which creates standard second-order filters like the low pass, the high pass, band pass, low shelving, all pass, and so on. One can also use the IIR filter node, which creates arbitrary filters. So rather than just second order, they can be any order, I think up to about 32nd order. The user specifies the coefficients of the filter and it's designed according to the specification, or user being programmer or developer. But the filters themselves are fixed. Once created, you can't change the parameter values. One can also create filters using the convolver node. Convolving with a filter's impulse response will generate a finite impulse response filter. So that's different from the IIR filters, or infinite impulse response. The FIR filters are ones where the output depends only on current and previous inputs. For IIR filters, output depends on current and previous inputs as well as previous output samples. And finally, if none of those three built-in nodes fit your needs, you can use an audio worklet to create your own filters. Well, equalization is just a form of filtering. It involves boosting or cutting certain frequency components in a signal, typically by applying several or many of these filters. The filters themselves, by the way, are linear and time invariant, generally by design, so fairly easy to work with. The origin of the term equalization comes from signal transmission over wires. So like old telegraph wires, they would find that the signal is severely degraded by the time it reaches its destination. Primarily, a lot of the high frequency content has been lost. So they boost that high frequency content with some filter in order to keep a flat frequency response where the frequency content at the output is equal to the input, to the frequency content at input. So it's equalization. Another term that's often used is to say that the content is colored if the frequency content has been significantly changed. So the goal is no coloration of the frequency content. Now, one of the simplest tools to do equalization, and a simple form or variation on graphic equalization, is the tone control. The idea with the tone control is there's just two controls, usually dials, which can be used to adjust the bass or low frequency content and the treble or high frequency content. And a listener will use this to adjust the sound to suit his or her taste. So the bass control provides a boost or a cut to the low frequencies, treble control, boost or cut to the high frequencies. And this suggests that we can use shelving filters. The low shelf for the bass, the high shelf for the treble. If the control is centered and not really adjusted, one should have a unity gain throughout, neither boost nor cut, and a pretty flat response. A lot of tone controls will also have a mid-range control, and it just controls frequencies that are neither very low nor very high. So the low shelf might have its cutoff frequency before the range of boost or cut of the mid-range. And similarly, after the boost or cut of the mid-range, then the high shelf kicks in. So this mid-range control is implemented with a peaking filter, giving similar behavior to the low and the high shelf, but now it's operating over a range of frequencies somewhere in the middle of the signal. Note also that all of these controls are not attempting to isolate particular frequencies. That is, they leave the frequencies outside of the frequency band of interest unchanged. They don't remove them, they're just intended not to affect the other frequencies. So the implementation of these is fairly straightforward. The filters are placed in series, typically from the lowest filter to the highest one, although the ordering shouldn't matter very much. Each one has a gain controlled for each one, usually implemented as a dial. So input audio comes in, goes through the low shelving filter, which does not change the high frequencies, then through the high shelving filter, which does not change the low frequencies, and then output. If there are three controls, the same principle applies: low shelving filter, then the peaking filter, then the high shelving filter. And so keep in mind here that these two here, mids and trebles, shouldn't really affect the low frequencies. So you pass them in series, one after the other. So that's the idea of the tone control. Let's now look at graphic equalization. It's in some ways just an extension of the tone control. It lets the user set the gains for fixed frequency bands. However, here, the bands are generally controlled with sliders, or faders, or range controls, different terms for the same idea, rather than dials. And there's many more frequency bands available than just the 2 or 3 in the tone control. Typical number for the amount of frequency bands are 6 to 40 frequency bands, so it can be quite a lot. Like the tone controls, the center frequencies are fixed in the design. The user is really only adjusting a gain value, the amount of boost or cut. But because that change is made with sliders, we have a nice property. The slider positions themselves represent samples of the magnitude response. If all of the sliders were down at the lowest value and only one was up to say 10 dBs, then that's what should be the output, removing as much as possible frequency content of everything else, but having a 10 dB boost at one particular narrow frequency range. So this form of equalization with many frequency bands controlled by vertical sliders gives a graphic representation of the magnitude response here, and hence it's called a graphic equalizer. Finally, the band distribution is logarithmic in frequency. This matches human perception. We are not necessarily much more interested in the 1,000 hertz from 1,000 hertz to 2,000 hertz than we are in, say, the 100 hertz from 100 hertz to 200 hertz. So we tend to perceive the amount of frequency content, and our interest is more for the low frequencies than the high frequencies. Therefore, we will use a logarithmic distribution. More on that now. So first, here's a little graphical user interface of a quite old graphic equalizer. You can see it's got 5 frequency bands, so 5 sliders here. They range, in this case, only providing a boost, 0 dBs, 5 dBs, 10, 15, and 20. And the corner frequency of each one is 62 hertz, 250, 1000, 4000, 8000. So very roughly scaling somewhat logarithmically. Now, I did mention that we'll scale it logarithmically, but how is that typically done? One approach, a very common approach, is that the center frequencies are equally spaced in octaves or some fraction of an octave. So this gives a logarithmic, not linear spacing. An octave is just a factor of 2. So 1 octave more than 1,000 will give 2,000, the next octave up will give 4,000, and so on. 1/3 octave spacing, another option, is spacing based not on 2/3, but 2 to the power of 1/3. So that if you multiply 2 to the 1/3 times 2 to the 1/3 times 2 to the 1/3, then you get a factor of 2. The best way to understand this is with a couple of examples. Consider 1 octave spacing starting at 100 Hertz. Then it would double. Each corner frequency that we're interested in would double. 100 Hertz for the lowest frequency band, then 200, then 400, then 800, then 1600 Hertz, or otherwise known as 1.6 kilohertz. If we did 1/3 octave spacing starting at 100 Hertz, we start with 100, then we multiply that by 2 to the 1/3, or approximately 1.26, getting 126 Hertz. Then multiply it by 2 to the 1/3 again, which gives us 159 Hertz, then again, which gives us 200 Hertz, which is the same as multiplying it by 2. So every 3 values, you double it. And so from 200 Hertz, 1 time, 2 times, 3 times, it doubles again. So it spaces up the frequency content just like 1 octave does, but finer divisions. Generally, the center frequencies or corner and cutoff frequencies, so the important frequency associated with each filter, those are fixed in the design. The Q values are also fixed in the design. The Q values could vary from frequency band to frequency band, but generally they are kept roughly constant. What that means is one frequency band on our log scale has the same shape in the filter as the next one, And as mentioned previously, the gains used for the user control are given in decibels. So how is this going to look? Very much like our tone controls. It's all connected in series, starting with a low shelving filter, then peaking filter, but rather than the 3 knob or the tone control with control of bass, mid-range, and treble, that one has a single peaking filter. Now we have many peaking filters, all the way up to the very last filter, which is typically high shelf. The low shelf and the high shelf at the beginning and at the end allow someone to apply boost or cut all the way down to 0 Hertz and all the way up to the highest frequency, which is the sample rate over 2, or the Nyquist frequency. Also, as with the tone control, these filters are arranged in series. So you apply the low shelf, then one peaking filter, then the next peaking filter, and so on. So at this point, let's look at a code example for a graphic equalizer. The graphic equalizer here is going to operate on noise signal. So first on the left, we have the HTML. On the right, we have the JavaScript. HTML, we have a button to resume the context if needed, because by default, you typically will not have an audio context started in the browser. Someone needs to turn on the sound on a web page. Then we have the range control or slider for the low frequencies, then mid-lows, mid-frequencies, mid-highs, and then highs. So we're going to have 5 sliders here, and hence we're going to use 5 filters. The rest of the code is just for recording audio right here, which relates to a previous lecture video that we had on loading and recording audio in the Web Audio API, but not really relevant for discussion of the graphic equalizer. Okay, now let's have a look at the JavaScript code. We first define the audio context. Then we have 5 lines of code here for defining the biquad filters that we are going to use for our low shelf, high shelf, and peaking filters. First, these could have been done as an array, and in which case the connections could have been done in a for loop based on the array and possibly further reductions, but I'm just being quite explicit here. The first biquad filter that we're going to use is the low shelving filter, and we're going to use our first corner frequency of 100. The corner frequencies are going to have a 1 octave spacing, so doubling from 100 hertz frequency to then 200, 400, 800, 1600. So our high frequency cutoff is high but not extremely high. After that first low shelving filter, the next 3 for the mid-lows, the mids, and the mid-highs are all peaking filters, and finally we end it with a high shelf. Now the Q values for each of these peaking filters we keep the same, and if you're designing your own, you might need to play around with Q values or give it some forethought or do some analysis to determine what Q values are going to sound best for your use. The idea is you do want your peaking filters to cover the whole of a frequency range, but not bleed over or interfere too much with other frequency ranges. Then we have a gain node, and this is so that the output of all of our filters will go into the gain node, and we will record the output of this gain node. We didn't really need a gain node here, it's just one way to record the output. And the gain node here, we're not changing the gain from its default value, it's 1, so the gain node itself doesn't do anything to the audio. Okay, the next 5 lines are callback functions. If the range control on the interface called lows gets changed, then change the gain value of this low filter. Similarly, if mid-lows get changed, change the gain value of the mid-low filter. And then the mid filter, the mid-high, and finally, if the gain or the range control associated with the highs on the interface changes, change the gain of the high filter. Peaking filters and low shelf and high shelf filters all have gain values associated with them, all given in decibels. So we don't need to do anything special here. We can directly modify the gains based on a range control on the interface. The next 2, and we're going to have final gain go to the destination. I'll talk about the other connections in a second. The recorder is just so that we can record the output of the filter. And we are using noise as the input to the filter. The noise was designed with an audio worklet, a very simple audio worklet that just streams out random numbers. So it's uniform distribution noise. And so that's where we load the module with the worklets, and we create our new audio worklet based on generating noise. So now we can connect the noise to the low filter, then with series connections, low filter to the mid-lows, and so on and so on. Finally, the high filter connects to our final gain, which is what we are recording. Okay, let's have a listen. So what you could hear there is different frequency bands being isolated and hearing just the mid-range noise or just high frequency noise as I adjusted everything on the interface. In a real graphic equalizer, the sliders will almost always be placed vertically, and you might tweak all of the parameter values to have more clear rendering. But let's see if it worked. So before starting the lecture, I recorded the output where I just had one slider up, so just the lows, then just the mid-lows, then just the mids, and so on. And we're going to plot it as a spectrogram using a tool called Sonic Visualizer, which is intended for analysis of audio signals and visualization of them, and it's freely available. And we're plotting the spectrogram. So on the y-axis, we have frequency on a log scale. On the x-axis, we have time. Color intensity is saying how much frequency content there is for that particular frequency range. So it's a bit like the power spectrum, or because we have noise as the input, like plotting the magnitude response. It's like the spectrum or power spectrum, but then turned on its side and taking snapshots of the power spectrum over time. So first we adjust the low frequency content. Bright color here means there's a lot of low frequency content. Then we move the low slider down and brought up the mid-lows. That's this one, then the mids, then the mid-highs, and then the highs. So it all seems to be working quite nicely. These horizontal lines here are just an artifact of producing the spectrogram and not really an issue, and might also be an artifact of how we recorded the noise. But we do get the right behavior here. There is a little bit of overlap between the regions here, and one can adjust the Q value to have more or less overlap. One other point you notice is that the frequency content is a lot stronger for our low shelving filter at the very bottom and the high shelving filter at the top than it is for our peaking filters. And that's due to the design of the filters in the Web Audio API. So one way to create peaking filters and bandpass filters is to combine a low shelf and a high shelf, or a low pass and a high pass. And in that sense, low shelving filters, low pass filters, high shelving and high pass filters can all be lower order than the peaking and the bypass and bandpass. But here in the Web Audio API, the low shelf and high shelf are the same order filter, and so they actually have sharper cutoff on that one edge than these ones do. So you can play around with the filters a bit to get them more similar, but it's inherent to the design of the low shelving and high shelving filters in the Web Audio API that they do a stronger job of having a sharp shelf associated with a given range. You can also adjust the gains here a little bit more to get them closer together. Okay, so there's a couple more points to mention about the filters. So just using almost any filter is going to affect the signal, but also these filters are not ideal. So here I'm plotting magnitude response for pretty high quality equalizer, where I have 10 bands and they each have a 12 dB boost. And in this example, you don't get a flat response, and you very rarely do. So there's actually some ripple here, some variation in the response over frequencies, especially at the extreme value there. And what is happening is each filter tends to affect, to some extent, the content outside of the range of interest. And so they're all overlapping, all interacting with each other. So they will have some ripple. Finally, there's a second design that can be used for graphic equalizers. Rather than low shelf peaking filters and high shelf in series, one can construct it with low pass, band pass filters and a high pass filter in parallel. The idea here is that each of these filters will isolate a frequency band. So you can apply a gain just to a range of frequencies without and remove all of the others. Here, we're showing a sort of idealized form of the bandpass filter, and it will remove frequencies outside of the range of interest. The only things of interest here is the corner frequency and the frequency band that we're working with, which is determined by the bandwidth of the filter. The bandwidth in turn is closely related to the Q factor or quality factor, because the quality factor can be given by the center frequency or corner frequency divided by the bandwidth. So it needs to be in parallel, because if you place a low pass filter in series with a high pass filter, the low pass has removed the high frequency content, giving almost nothing for the high pass filter to work with. The high pass filter will also remove the low pass content. But instead, you isolate each frequency band, apply the gains, and sum them back together. In the Web Audio API, the low pass, band pass, and high pass filters don't use a gain control because they're just isolating a range of frequencies. They're not applying a boost or cut. So your design would need to connect the output of a low pass filter to a gain node, and same with the band pass filters and the high pass filter, and then the output of all of these gain nodes should be summed together, perhaps in another gain node or straight out to the output. The gains also for a gain node are linear, and we would like on the interface the user to be able to adjust gain in decibels. So you would need to convert the value on the interface from decibels to linear units. But otherwise, it's pretty simple to do this parallel implementation. And there may be lots of good reasons to do it, related to precision, related to latency in series implementations, and so on. So that concludes this lecture on graphic equalization in the Web Audio API. I hope you found it useful, and do check out the code on GitHub and the book that goes into far more detail on programming for the Web Audio API. As always, if you have any questions or comments, please do get in touch. Thanks very much.